All right, now it's time to move some things with some torque. So if I've got a girl sitting on the edge of a rotating platform, and I want to apply a torque to the edge of this, so I will put a force acting at the edge of this, and I can calculate the magnitude of that torque by saying that equal to the force multiplied by the radius of the disk. Okay, now why does that work? Well, if I look at this from top down, there's my circle. Okay, and my applied force will be at the edge of it, right there. I'm trying to draw that parallel or tangent to it. And of course my radius is going to be this direction here. So my force multiplied by my distance to the point of rotation would be force times radius. That's my torque. So now let's consider what's happening here. Well, there is inertia. The girl, she's going to look like she's a point going around it. So her moment of inertia, I, is going to equal m times her distance squared. Right now she's 1.9. Now the platform is a rotating platform, and use calculus to derive that equation. So the moment inertia of the platform is 1/2 mr squared. Okay, and you would need to know the radius of the platform there, which I think is 1.9 because I think the girl is at the edge. Okay, so let's call that one I1 and let's call this one I2. So I'm going to set torque also equal to I alpha. Alpha being the angular acceleration. So this one's like F equals ma. The moment of inertia looks like mass. It works just like mass. Okay, so what's that going to look like? It'll be force times radius equals I1 plus I2 and multiplied by alpha, which would be the angular acceleration of the system. Now let's say that she's moving around at some kind of omega. We'll call that omega 1, and we remove the force. What if she moves closer to the center? Okay, well when she does that, her radius will change. So the I of the girl will still use as mr squared, but let's call that mr prime. Okay, and we'll square that. So she's going to have a new, okay, moment of inertia. So then we use the conservation angular momentum. Remember, momentum angular has an L symbol to it. So we'll say L1 is equal to L2. The beginning angular momentum must equal final angular momentum. Okay, so what is that going to look like? Well, it'll be I1 plus I2 multiplied then by omega 1. Because really this equation comes out to be I1 omega 1 equals I2 omega 2, because that's what angular momentum is equal to. So L is equal to IW. That has to equal the final, okay, angular momentum. So I'm going to have I1 plus I2, and I'll put a little prime on that. Okay, because she has moved closer to the center. Multiply omega 2. So we can find how fast this will be spinning when she moves to the center. So it's kind of reminiscent of the ice skater. The girl has her arms out and she's spinning a certain velocity, and then she pulls her arms in closer to her body and she spins a lot faster. So that's kind of what that's analogous to. Okay. Now what about rotational kinetic energy? So kinetic energy rotational is like 1/2 I omega squared. Okay, kinetic energy regular, we call it translational, is equal to 1/2 mv squared, right? Okay, and that's why that works. And let's look at linear momentum. Momentum is m times v, right? So m is like I, v is like w there. So if I want to figure out how much work she does to pull herself in, the work done will be kinetic energy rotational 2 minus kinetic energy rotational 1. So you'll go 1/2 I omega squared. In the first case, beginning momentum of inertia is going to be I1 plus I2 multiplied by whatever the beginning omega angular velocity was. And that's what will go there. And the final kinetic energy will be I1 plus I2 prime, because the girl's closer in, and that final angular velocity would go there. We're going to find out that this is some kind of positive number for joules, because the work she does to pull herself in is what's making her go faster. All right. Next, what about the relationship between linear momentum and angular momentum? Say we have a door here, okay, and Buddy is going to run and land on the door and going to make the door swing outwards. Okay, so let's look at this from a top-down view of it. Okay, so here's our door. Okay, that's actually a side view of it. Okay, our door has a beginning moment of inertia I. Okay, and let's see, here's our hinge. I'll put a little circle here for our hinge. Okay, so I1, okay, is going to have some kind of formula associated with it. And then Buddy is going to land on it. And it's going to be like a collision, so imagine him being like a little circle because all of his mass is going to come from one central location from him. So we have I1 omega 1 still has to equal I2 omega 2. Okay, so the beginning angular momentum of the door has to equal the final angular momentum of the door. But we also include, okay, Buddy in this situation. So what's the relationship between linear momentum and angular momentum? Well, the way it works is this. L is equal to regular momentum multiplied by R. Okay, the distance the object is from the point of rotation. So let's give Buddy an initial velocity of V, and he's got 5 kilograms. We'll just call that M. Okay, so, and he's 1 meter from the center of rotation when he lands on the door. So his angular momentum L is going to equal mv times r. Okay, and in this case, he's got, what, 5 kilograms of velocity. Let's say he comes in at 3 meters per second. So 5 times 3, and he happens to be 1 meter from the door center of rotation, so 1. So initially, the door is not moving at all. Okay, so the I1 omega 1 is actually coming from this. Okay, so what would that be? 15 would be the number there. So we're going to have mvr is going to equal let's go I Buddy plus I of the door multiplied by omega 2. Okay, so how do we get the I values? Okay, so this would be I of Buddy. This would be I of the door. Well, again, Buddy is a point mass as he rotates around. All the mass looks like it comes from one center place from. That's why he's represented just as a circle here. So Buddy is going to be mr squared. Okay, and the I of the door, okay, is going to have an equation associated with it. And that equals 1/3 ml squared for the door, so that'll be the length of the door. So again, this equation is valid except this part here, since the door is not moving initially. We have to look at the angular momentum of Buddy as he comes in. He is going in a straight line, but the relationship between linear and angular momentum is this equation. So linear momentum multiplied by the distance the object is from the point of rotation when it collides with it is what angular momentum is actually going to be. Okay, and that's how you handle it. And our next video, okay, we'll deal more with rotating things and moment of inertia.